I think we are nearing to the 5 minute mark. So let me introduce Akshay, who has agreed to give us a seminar on representation learning and exploration in reinforcement learning. So Akshay is a principal researcher at Microsoft Research in New York City. He also spent 2 years as an assistant professor at Amherst, and previously he was also a postdoc researcher at MSR. So we are very excited about Akshay, and he is excited himself about interactive learning, learning about settings that involve feedback-driven data collection, and his recent work has focused on decision-making problems with limited feedback, including contextual bandits and reinforcement learning. With that, Akshay, we are very excited to hear you, and please take the stage away.
Thanks, Pulkit, and thanks everyone else for coming. This is should be a really fun talk. So today, what I'm going to try to do is tell you about some work that me and a bunch of colleagues have been working on, trying to sort of discover the foundations of reinforcement learning in like complex environments, and we'll see some of the core issues and some algorithmic insights that we've sort of come up with, and many open directions. I think we'll also talk about those. Okay, let me make sure the slides are working. Okay, so we've been calling this rich observation RL. I think on the empirical side, we've seen a lot of success in deploying reinforcement learning algorithms in situations where the agent operates on like extremely high dimensional sensory inputs. So we've seen, deployments in gaming, things like this is a picture from Minecraft that my colleagues in Cambridge have been working on. We've seen a bunch of work or excitement around what Ben Recht has been calling perception-based control. And these are things like where you have a robot and the robot is operating from a camera or a LiDAR sensor. And we've also seen a lot of excitement, but perhaps not too much realized here on deploying reinforcement learning in personalization settings like in dialogue systems. And when you think about these problems, we've seen a lot of the successes are, I think, if you think about them kind of like skirting the core RL problems and instead leveraging inductive biases to get things that we can deploy right now. So I would say these are things like using a simulator, using imitation learning, doing reward shaping, these kinds of things. And I think right now, if you wanted to actually get some reinforcement learning thing going today, you would probably need to leverage some sort of inductive bias or some sort of domain expertise in the form of these kinds of things to get things going. But these are kind of skirting the core RL issues. So a basic question that I've been thinking about is, how do we address the core RL problems without any of these other ideas like imitation learning and so on? And so this is sort of what we want to do. We want to develop provably efficient sequential decision-making methods that scale to these complex domains. And I hope you believe that this is a useful thing to do. Let me first tell you why these things are kind of hard to get going. So if you want to address the core RL problem, you have to simultaneously address three sort of capabilities. So these are exploration, credit assignment, and generalization. So exploration is just that the agent needs to be very intentional about what decisions it's going to make so that it can acquire information to learn further. Credit assignment is when you make a sequence of decisions and you see some outcomes, you need to be able to understand which of those decisions were important for causing those outcomes. So John Langford likes to say, which move lost you the game of chess? And generalization is what probably most of us are very familiar with from supervised learning. This is just the ability to use experience you've seen in one situation to make decisions in another situation. And this is what supervised learning is quite good at, but there's some issues in the reinforcement learning paradigm. Okay, so if you are thinking about the foundations, maybe the first thing you might want to ask is, can we address two of these capabilities at the same time? And we've been working on those kinds of things for a long time as a community, and we actually have quite mature technologies for addressing two of three things. So addressing exploration and credit assignment, we have quite a large body of work on what's called tabular Markov decision processes or tabular reinforcement learning. And these are things that, they have very sophisticated exploration strategies, but these algorithms maintain a table of statistics about states and actions. And so they do not actually generalize. Perhaps what's most deployed in practice are policy search methods. And these are addressing credit assignment and generalization, but not that clever about exploration. And one thing that like my group has been working on a lot is contextual bandits, which is addressing exploration and generalization. But these things are not designed to solve long horizon problems. And so they're not really addressing the credit assignment issues. So these are sort of the three capabilities. And what we've been working on is trying to design algorithms and understand how we can possibly get algorithms that solve all three of these issues at the same time. And just to kind of drive this point home, let me just show you like a pathologically difficult RL problem. And it'll be like a nice sort of grounding for the rest of the talk. So this is going to be called like a combination lock. So the agent starts uniformly in one of two states. This is S1A and S1B. From each of these states, there's going to be one good action and 9 bad actions. So, this is going to be the good action and it has some label, and this is going to be the good action from S1B. These two labels might be different. And the good action transitions you stochastically to either S2A or S2B with probability half-half. And then bad actions transition you to S2C deterministically. And this process repeats for 100 time steps. And the good action, from S1A will be different from the good action from S2A and S2B and so on and so forth. And if you make it down the two good chains, so you end up in S100A or S100B, and you take the good action, then you're going to accumulate a very high reward. On the other hand, if at any time you fall into the C chain, you're going to accumulate a low reward. Okay, so this is the kind of problem that we're thinking about. This is somehow pathologically very hard, and it exhibits a lot of the issues that reinforcement learning algorithms struggle with. So the first one maybe is anti-shaped reward. So until you discover that there's a high reward over here at the end of the chain, you might think that the best thing to do is actually to fall down right away into the C chain. And so you have to sort of overcome this reward that's encouraging you to go to the wrong place so that you discover the optimal reward. Another issue is you have stochastic dynamics. So this precludes the use of like open loop control policies. You really have to look at where you are before you decide what to do next. And the other one is you have a fairly long horizon of length 100. So these are some issues that, probably a lot of you are familiar with. This problem, as I've written it right now, is actually not very difficult because there's only 300 states. There's only 10 actions per state. This actually falls in the purview of tabular reinforcement learning. And so there are algorithms that solve this problem. So let me make this a little bit harder. So what I'm going to do is I'm going to endow each state with a distribution over like images. So here, this is like, very high dimensional image, and the agent will never observe the state. Instead, the agent will observe these images that are generated stochastically from the states. So this is what I'm going to call rich observations. And now you have a real problem. These tabular MDP kind of algorithms, they maintain statistics on the individual observations. They will just never succeed because the observation space is just way too high dimensional. And indeed, if you run like other methods, like say PPO, it just fails miserably here. So we ran PPO, we gave it like 1 million episodes to run, and it like never makes it past the fifth step in the chain. So this is what I'm showing you here is the visitation like frequencies over here. So green is like where it mostly ends up, and white is where it never made it. And we'll revisit this one later. So this is sort of the kinds of problems that like pathologically we'd like to be able to say something about. And maybe a bit of an overfitting solution is to observe that you have this high dimensional image, but there is this true latent state space that's sort of governing the dynamics of the world. So if only we could map our high dimensional images into these latent discrete states, we'd then be able to run a tabular MDP algorithm, and we'd be great. So this is like this is a form of representation learning. You have this high dimensional image, you want to learn a representation for the environment, which is this latent state space that enables you to run simpler methods. And so this is sort of the way that like I'm thinking about these representation learning problems in reinforcement learning. And there's sort of like 3 points I want to make here. So the algorithms we're going to develop are like explicit representation learning algorithms. So they're going to explicitly try to decode the state from the observations and then apply like a tabular MDP algorithm on the latent state space. And I like this approach from a conceptual perspective because it kind of decouples the dynamics of the system, which are necessarily simple in this example, from the observation process, which can be sort of extremely complicated. And due to the fact that the observations might be extremely complicated, you really have to use nonlinear function approximation to succeed. So you have to use deep learning here. And the challenges are that, well, representation learning and exploration are like fundamentally intertwined. So you can't learn a good representation without getting a data set that's representative of the problem. But maybe you can't get a data set that's representative of the problem without learning how to explore. or without having a representation because it's required for you to explore. So the challenge is how do you, break this intertwining sort of thing. Okay, so but before we get into the details, I want to talk about like one other issue, which is catastrophic forgetting. And this is going to motivate the types of solutions that we're going for. So this is an experiment that some of my colleagues ran. This is like the combination lock I showed you before, except it's now what they call bidirectional. So you start and you can choose to enter the upper chain or the lower chain. And then you face this problem I showed you before. And only like in this example, only the upper chain gets you the optimal reward if you make it to the end, and the lower chain will get you like half of the optimal reward. So something suboptimal. And so my colleagues, they set up this problem and they ran like algorithms with good exploration strategies. So here, this is like traces of their run of this random network distillation exploration bonus. And what I'm showing here is like the heat map of the coverage of the learned policy. So, as it starts, it's exploring the upper chain, it's making it somewhere, and then it sort of like snaps to the bottom chain, and then it covers the whole bottom chain, but it sort of forgets that the top chain exists at all. And the chain that it snaps to is basically chosen at random. So half the time it just gets the suboptimal reward. And they see this in the experiments. And this is sort of highlighting this issue of catastrophic forgetting because the R&D exploration bonus forgets that there's some stuff that hasn't been explored yet. And it suggests that we sort of need to be more deliberate about keeping global visitation information or global coverage information. And the way we're going to do this is with a policy cover. So this is just a collection of policies that are intentionally trained to cover the whole state space. And we sort of like freeze training them. So, we have a policy, we're going to checkpoint it, and we're going to stop updating its parameters. And that's going to get us to, let's say, the top of the first chain. And then we're going to have another policy that's going to get us to the bottom chain. And this is going to be great because we're going to be able to train these in a reward-free manner. There's going to be no external reward signal. And at the end of the day, we're going to be able to use these policies to gather the data set that's going to enable us to optimize any reward function ex post. So that's the kind of solution concept we're going to go for. All the methods I'm going to talk about today are just going to discover a policy cover. And actually, all the methods operate in a very similar algorithmic framework. So this is going to be, I'll call it a forward scheme, and I'll explain why. And it's going to be doing reward-free representation learning and exploration. So you're going to just start with a policy cover that's just, let's say, a random policy. And you're going to repeat the following steps. First, you're going to use your current policy cover, your current set of policies, to collect some new experience. You're going to use your new experience to refine the representation that you have. And then you're going to use the representation that you just like learned or refined to update the set of cover, the cover that you have. And hopefully, as you proceed, your representation is getting better. Your cover is able to discover new places in the state space. And slowly you'll cover the whole state space with a representation that's sort of good enough for you. So the picture that I like to keep in mind is this sort of layer by layer approach. So that, in the H iteration of this procedure, the policy cover, which I'll usually denote them by row. So row H will be trained to visit all the states that are reachable at time step H in your problem. And so you're going to roll in using your policy cover, and then you're going to maybe take a random action. And that's going to give you a data set over the state at time H, the action at time H, and the state at time H+1. And you're going to maybe use this triple to learn a new representation. Okay, maybe you'll learn a representation for the states that are reachable at time H+1. And then you're going to update the policy cover using this new representation. We'll set up like some reward bonuses or something like that. And what you're going to get after you use you update the cover is going to sort of like boost straight through to the H plus first time step. So it's going to get good coverage over all the states that are reachable at time H+1. And then you proceed, layer by layer. And that's why I call it a forward algorithm. You're going to learn stuff for time step H, then learn stuff for time step H+1 until the end of the problem.
Actually, can I interrupt for a question?
Yeah.
So over here, is the goal to learn a good compression, or are you trying to learn something more than a compression? Because if I'm trying to cover all possible state spaces, right?
Yeah.
It means I cannot ignore any information, right?
Yeah, that's right. So I'm being a little bit vague about what I mean by coverage. What I mean by coverage is sort of you induce a distribution that has a good density ratio to any other. So if your problem has like bottleneck structure, you don't actually have to visit every state with good probability, because some states maybe just cannot be visited. I think we are basically going to learn a good compression, but actually what I what I think really matters is your ability to have a good density ratio with respect to any other policy, because that is what enables you to run like offline reinforcement learning methods after the fact. So I'll tell you the theorems. They'll have both of these kind of properties. Hopefully it'll make sense in a bit.
Okay.
Okay, so this is the basic algorithmic framework. And actually all the algorithms I'm going to talk about are instantiations of this framework. So if we have time, I'll get to 3. The first one is this algorithm called Homer. It uses a representation learning objective based on contrastive estimation. And it uses a planning objective to learn the policy cover. We just use sort of like a dynamic program. This is actually a very classical thing over here. And the model in which we analyze it is this block MDP, which is a formalism for the combination lock problem I showed you before. The second one operates in a more general model. So this algorithm is called FLAMBE. It operates in this low rank MDP, which I'll tell you is more general than a block MDP. The representation learning objective is actually very straightforward. It's just like density modeling. So it's very model based. And the planner is a model based planning algorithm that uses a very special reward bonus based on this elliptical or ellipsoidal argument. And the last one is, it also operates in the low rank MDP. It's called Moffle, some silly name. And it shares a lot of components with FLAMBE, except the representation learning objective is a little bit different. So here we're going to use sort of like an adversarial training kind of objective. But the planning is going to be very similar. Okay, maybe now is a good time to pause if there are any other questions. I think probably we won't get to all 3, but that's okay. Okay, great. So let's start with Homer. So this is joint work with Dipendra Misra, Michael Hanaff, and John Langford. So let me start by formalizing the block MDP. So this is going to be, this formalism for this combination lock problem I showed you before. So the way it works is that the agent operates on this. Sorry, the problem has a discrete latency. Hello.
Sorry, I think someone just got mute.
Okay. Yeah. So the problem has this discrete latent state space. So the way I think about this is you're in like a visual grid world problem, and the discrete state is the grid cell that the agent is in. The agent does not observe this grid cell. Instead, the agent has a first-person camera on its head and sees this high-dimensional image that is sort of generated from the grid cell that the agent is in. So the agent is going to operate on these rich observations. So you see this observation X1, you take an action A1, and you transit to a new discrete latent state, S2. And this transition depends only on the latent state and the action. It does not depend on the emission. So that's pretty important. And then so it repeats. Okay. So this is sort of the problem. And the emissions are going to be extremely complicated. You should think about them as images. And this is really going to necessitate the use of nonlinear function approximation. On the other hand, as I've stated this problem so far, it looks a lot like a POMDP. I do not want you to think about it like a POMDP. So what I'm going to assume is that the latent states are actually decodable from the observations. So there's no partial observability issue. This is really an MDP on the observations directly, but it has this nice compression structure under the hood. Okay, so what I mean by decodable is that each state is associated with a distribution over emissions, and those emissions can only be produced by one state. So you can actually map from the emission to the hidden states directly. Excellent. So this is the model. So let's revisit this sort of forward algorithm. So this one is really going to be layer by layer. So we start with this empty policy, it just doesn't do anything. And for each time step, we're going to use, okay, so at time step 0, we use our empty policy. We just take the first action at random. And what we're going to do is we're going to learn a representation for time step 1. Okay. And then we're going to learn policies that visit time step 1. And then we're going to rinse and repeat. So now we're going to use the policies we have for time step 1 to roll into time step 1, take the second action at random, and learn a representation for time step 2, and keep pushing forward in this manner. So I think that the fun part here is how do you learn these decoders or learn this representation? Oh yeah, so the intuition is that row H, the cover for time step H, ensures good coverage at time H. When you take an action uniformly at random, you actually have reasonable coverage at time step H plus 1, but you don't want to chain random actions together because then your coverage probabilities are going to be exponentially decreasing. So you want to somehow use the fact that you have reasonable coverage at time step 1 to later get much better coverage at time step H plus 1. So you want to save this factor of the number of actions. So yeah, the key questions are how do you learn this decoder? That's kind of the fun part. we'll rely on some sort of classical techniques to compute these homing policies afterwards. Okay, so learning the decoder, actually, this is sort of how this whole project started. We read Deepak and Pulkit's curiosity-driven exploration paper, and we actually invited Deepak to come visit us, and he told us about it, and we started thinking about all these sort of self-supervised prediction methods. So yeah, so the main challenge is that you don't observe the latent state. So you have to use some sort of auxiliary loss to try to learn this decoder. So we thought about a bunch of these methods. The one from the curiosity-driven exploration paper is the first one I'm listing here. So here you try to predict the previous action from the current and the previous state. We also thought about some other procedures where you train a decoder for the previous time and you try to predict the previous action and the previous decoded state from the observation. And so we thought about these things for some time. We actually came up with some, so we like had this like mathematical abstraction for what these methods are doing. And then we came up with some situations in which they fail. So maybe it's worthwhile to go through this one. So let's say we're trying to, the way we're going to learn the representation is we're going to predict the previous action from the current and the previous state. And what I claim is in this MDP over here, this will lead you to collapse these two states, all the things in gray together. So S1 and S2 will be collapsed together. S3 and S4 will be collapsed together. And in particular, S7 and S8 will be collapsed together. And this will be kind of bad because in this problem, there's actually a policy that visits state S7 with probability 1. But if you collapse them together, you will not be able to discover this. And the reason is that if you're, okay, in the first time step, if you want to learn how to predict that first action from the 0th and the first state, you can see that if I'm in S3 and S4, no matter where I come from, the previous action was A1. And if I'm in S5 and S6, no matter where I came from, the previous action was A2. So I can safely collapse all these things together. And something similar happens at the next time. And so you will collapse these two, and then you will fail to have good coverage over S7 and S8. So this is sort of like the way that I like to think about some of these things. I like to read the empirical literature. I read those things. I try to come up with little examples to for me to understand what's going on. And sometimes these are quite revealing to me. So you know, we thought about these kinds of methods quite a bit. We also thought about sort of unsupervised learning approaches. So one approach that we've seen in the literature a lot is this using autoencoding. This one, I mean, it seems to actually work pretty well in practice, but I just have no idea how to understand this in theory because these autoencoding approaches can really just memorize noise, and they will not discover the state at all. So that's what I'm showing over here. You have, you know, the state is the first bit. There's a bunch of random Bernoulli bits attached. It's actually the optimal thing to do is preserve a noise bit in terms of your reconstruction loss. So we didn't really understand how to analyze any of these things. But what we did figure out how to do is to use a contrastive learning objective. So here's what the procedure does. So you're going to roll in with your policy. You're going to visit some state. You're going to take an action at random, and you're going to see this triple x1, a1, x1 prime. You're going to roll in again. So you're going to see another triple x2, a2, x2 prime. These are going to be different in general. And now you're going to have this observed transition, x1, a1, x1 prime. And you're going to create a fake or an imposter transition by splicing these two triples together. So you're going to take x1, you're going to take a1, and you're going to splice on x2 prime. So this is something that actually didn't happen in the real world, as far as you know. And what you're going to do is you're just going to train a model to predict which ones are real and which transitions are fake. Okay, so that's the contrastive loss. And so this is sort of the objective function. So y is the real or fake label, and xa and x prime are the transitions that you have in your data set. So you can definitely collect this kind of information. And the only thing that's special here is that this model that we're using has this sort of quantized structure. So your model takes the state, the action, and the next state. The first thing it does is it actually passes the next state through a discrete bottleneck. And then it maps to the, tries to predict if it's real or fake from this discretized intermediate representation. And okay, this discrete bottleneck is the decoder. Okay, so that's sort of the contrastive procedure. And yeah, that's the discrete bottleneck. And another thing that I found very helpful when thinking about these problems is just to think about sort of the Bayes optimal predictor for, you know, I set up a regression problem. It's useful to think about whether this discovers the right information at all. So this is sort of this Bayes optimal calculation. So the Bayes classifier for this contrastive problem is it's the true transition normalized by the transition plus some prior probability. This is the probability that you see x prime under the noise distribution. And if you rearrange these things, so first of all, observe that this depends only on the true state of x prime, which sort of justifies the use of the bottleneck. And so what you can deduce is that if you bottleneck two states to the same value, then this ratio of the transition operators is the same for both of those two states for any incoming state action pair. And once you have this structure, you can also deduce that the probability of visiting these two policies, these two states by any policy is coupled by some ratio. So if you maximize the probability of hitting one, you will automatically maximize the probability of hitting the other. So these two states are fundamentally linked together as far as the dynamics are concerned. And so this is what we call the kinematic state abstraction in the paper. And so this structure is very useful as far as exploration is concerned, right? You really can say, let me just try to hit one of these and you'll hit the other one for free. And this will give you good exploration. So this is a bit of a tangent, but one thing that we found quite annoying about this quantization structure is that it's kind of hard to train a neural net with discretization in the middle. You get no gradient. So there's another approach that we also thought about, and we've been thinking about this also in the absence of reinforcement learning, just for like self-supervised representation learning. And so here's the approach. So you solve this unquantized version of the contrastive problem. You just get a predictor f hat. And then you're going to sample some landmark state action pairs, and you're going to create a vector valued embedding by looking at the values of your learned predictor on these quote unquote landmark points. So this is a vector where you loop over your landmarks and you pass everything through your predictor and you get a scalar at the end. And then you just do a clustering in this embedding space. And this embedding space can be relatively low dimensional. And what we'll show is that these things are actually quite separated. And so now you still have a discretized abstraction at the end. So this is nice because these things are easier to train. You have no discretization during the training stage. On the other hand, you still have to discretize ex post. And so we'll see how to deal with that in the second part of the talk. And I think maybe the point I'm trying to make here is like representation learning is a huge thing on the empirical side, but there's like a huge theory practice gap in understanding what representation learning is doing, why it's working, and these kinds of things. So we're trying to work on those. This is a bit of a tangent, but it would be awesome if other people want to also like help out. I think there's a lot to understand here. Okay, so anyway, now we have this decoder. It's quantized for now. So what we're going to do is we're just going to set up these reward bonuses where the ith reward bonus is just 1 if you hit a state whose decoded value is I. So remember, the decoder maps to a discretized state space. So this is a pretty reasonable thing to do. And we just use a model-free planner to maximize this reward function. The one we used in the paper is this sort of classical thing called policy search by dynamic programming. It just works by solving a planning problem by a reduction to contextual bandits. And I think it's very classical. I'm not sure if everyone knows about it. We didn't know about it before we did this paper, or John knew about it and none of the rest of us did. So I thought it was like worthwhile to go through. So here's the idea. You're going to learn from the last time step to the first time step. And the way you're going to do it is you're going to roll in. So when you want to learn the policy that operates at time step 1, you're going to roll in with your policy cover that we already have to get a good coverage over time step 1. Then we're going to take a random action and we're going to solve like a one-step RL problem, which we also call a contextual bandit problem, where the reward function is based on a Monte Carlo rollout using the learned policy we computed in the previous iteration of this dynamic programming. So we already knew how to maximize this reward function from time step 2 onward, and that's this policy pi hat s. And so we just solve these, when you solve this contextual bandit problem, you learn the near optimal policy for maximizing the reward from time step 1, and this will allow you to go backward one time step in the dynamic programming. So that's this policy cover kind of idea and this PSDP algorithm. Okay, so what do we prove for this Homer thing? So we're going to assume that we have a function class of candidate decoders, and the true decoder, the true mapping from the emissions to the true state space, is in this class. So this is a form of realizability. And we're also going to assume that these latent states can be hit by some policy with probability at least eta. So I just want to point out that this does not make exploration trivial. So this is for each state, there exists some policy that hits it with probability at least eta. It does not mean that, say, random exploration will give you good coverage at all. And what we show is that this algorithm learns to cover the latent states. And for any reward function, it can find an epsilon optimal policy using a number of trajectories that scales polynomially in the latent state space, the number of actions, the time horizon, 1 over this reachability parameter, 1 over the accuracy parameter, and logarithmically in the cardinality of the set of in the number of decoders that you have. And this log size of phi type object can be replaced with various other statistical complexity measures using standard like uniform convergence kind of arguments. And the algorithm runs in polynomial time, assuming you can solve this like contrastive learning problem and this contextual bandit problem that we use for planning. So that's the kind of thing we're going to try to prove. Let me also just point out that this S here is the number of latent states. So there's no explicit dependence on the number of observations. Now, if you have a more complicated observation class, you probably need a more complicated decoder class. But hopefully this is allowing you to incorporate the inductive biases that you need, or use neural nets and not pay for the number of images in the universe. Okay, so let's return to this hard exploration problem. This will be very quick. We've seen this one before. So again, I'm going to show you here the coverage of these algorithms after you've run them for 1 million episodes. So PPO just completely fails. It doesn't even make it to time step 6. We ran this random network distillation exploration bonus. I think with PPO under the hood, we tried a couple of different optimizers. And this actually worked kind of well, but it seems to have a bit of high variance. So there's some issue where the exploration bonus sometimes is repetitive with something you've seen before, and so you stop pushing forward. So this one sort of gets to like time step 28. And I wouldn't be showing you this if Homer didn't just like snap to the answer. So Homer just successfully explores all the time steps. We actually can also kind of recover the latent dynamics model. But this is the sort of thing I would want. I want a policy, I want an algorithm that can induce a good coverage over the entire latent state space. Okay, so that's the block MDP. And let me just summarize with some pros and cons. So it allows you to accommodate nonlinear function approximation. It's still tractable, and it can model many rich observation RL settings. So like these visual navigation things, I think it's pretty reasonable for them to model them using this kind of framework. And Homer demonstrates that you actually can solve these problems. It's also gaining interest. So I saw that Dylan and Sasha are here. So they have a paper on the block MDP, which I think is pretty cool. So you can ask them offline, or I would recommend you read their paper. I've sort of hinted at some of the things I don't like about this. So I think a discrete or finite latent state space is kind of annoying because it forces you to do some sort of quantization. Now you can do this in your training, which is very difficult, or you can do it after the fact. Both are not that desirable. And another thing that I think we probably shouldn't need is decodability of the latent state. It should be totally fine for you to just be able to approximate the Q functions and the value functions and so on. And perhaps you don't really need to be able to decode the state to succeed. So this is what we're going to try to address in the next part. I see there's one question. How do you decide on the number of latent states? I think you can do some sort of model selection stuff. We only ran it on this problem where we know that it's 3. So we actually, there's still a lot of questions about getting these things to work in practice, certainly. That's a good question.
Can I also ask one more question, Akshay?
Yeah.
So one of the motivations you talked about was that if you use these action prediction schemes, states are getting clustered together, right? Mm-hmm. You couldn't guarantee exploration or visitation to all of those states, right? And then you talked about autoencoders, in theory could solve it, but you don't use it, but you use contrastive learning.
Yeah.
Right? So is it because it's hard to get guarantees when you're using autoencoders, or is it because autoencoders states which will also guarantee this, it wouldn't collapse states together, right? So in theory, they should perform similarly.
Yeah, so I think there's some theory practice gap here, certainly. I think autoencoding, so one thing that contrastive estimation is doing is it's using the dynamics information. So autoencoding, as I understand it, is not actually using information about the dynamics at all. And you do want to use information about the dynamics when you learn your representation. So I think there probably are autoencoding schemes that you try to predict the next state using a function of the current state.
Yeah. And
that is probably much better. And that's actually something I want to try empirically, or if you know people who've done that, I would love to hear about it. But yeah, so I think it's some of these things are like we haven't like we couldn't analyze them, or some of them we have counterexamples and so on. I'm not trying to say that those things don't work at all. Yeah.
Okay. Yeah. Maybe we can take this up for discussion. After.
Yeah. Yeah. Okay. So let's get to the more general model. So this is this FLAMBE algorithm and the low rank MDP. This is joint work with Alek Agarwal, Sham Kakade, and Wen Sun. So here's this more general model. So you have this transition operator, And I like to think about this operator as a matrix where the like rows are indexed by state action and the columns are indexed by the next state. And the low rank MDP, when you write this as a matrix, kind of the obvious low dimensional structure is to posit that it's low rank. Okay, so that's what we're going to do. So we're going to assume this matrix has a factorization into a rank D. It's rank D and it has this sort of factorization. And the phi map is going to be the sort of latent feature representation. So what I'm going to assume is that the embedding dimension, which is the rank, is D. And it's much, much less than the number of observations. And this phi feature, so this phi thing associates a D-dimensional vector with every state action pair. And that's going to be the latent representation. So we're going to try to discover this thing. Okay, so just some random points. The block MDPs happen to be low rank. This is very easy to see. I'll skip this. There's another way to think about this model beyond this, as going beyond decodability. So if you think about this feature map phi as being on the simplex, so this induces a distribution over these D coordinates. And if the rows of this other factor are also in the simplex, then you could think about this model as you sample a latent variable Z from the discrete set 1 to D from this feature mapping phi of Xa. And then you sample the next state from a distribution parameterized by the latent variable. So this is actually a model that's been proposed before. And it's very, very close to an HMM. So you have these latent variables Z, they're not decodable from the observations, but it's not an HMM because you forget the previous stuff when you see the new observation. So again, we're still not dealing with partial observability, but we are sort of moving beyond the ability to decode the latent state exactly. Okay, so why should we care? Well, this model has gained a lot of interest from the RL theory community. So we have efficient algorithms if the feature map is known in advance. We also have some evidence that these sort of problems are statistically efficient, even in the representation learning setting, where you don't know the feature map in advance. But perhaps more practically speaking, this gives you a continuous latent representation. This feature map phi is not posited to be discrete or anything like that. And so this will avoid some of the issues that we had with Homer. So it'll be closer to practice, perhaps it will give us more empirically viable algorithms. So that's why I sort of got excited about this representation learning in the low rank MDP. So yeah, let's revisit our algorithmic scheme. This one is going to be model based. So we're just going to start with a policy that's just random. And we're going to repeat this process for a bunch of time steps. We're going to use the current policy and we're going to, so these policies are, it's not going to be a forward algorithm actually, but you're just going to take your current policy cover and you're going to interrupt it at time step H and take the next action at random. And that's going to give you a data set like state at time H, action at time H, state at time H plus 1. And what you'd hope for is that this gives you good coverage at time H and H plus 1. And then you're going to learn the dynamics from H to H plus 1, just like using density modeling. You're just going to learn the whole dynamics. So that's model based. And then you're going to use your updated dynamics model to compute a new exploratory policy. And hopefully this one is sort of getting you new and better coverage. Okay, so these are the sorts of questions we need to answer. How do you learn the dynamics? How do you measure the coverage? And how do you compute these exploratory policies? So it's kind of complicated, but you have to think about 4 time steps at the same time. So to learn the dynamics, I'm just going to do maximum likelihood estimation, but many other things are possible here. To measure coverage at time H, we're going to use the true latent features at the previous time. And to compute the exploratory policy, we're going to maximize the learned features 2 time steps beforehand. Okay, so you have to think about 4 time steps. So H minus 2, H minus 1, H and H plus 1. The first step is going to operate over here between H and H plus 1. And we're just going to do density modeling over here to learn the dynamics. Now we want to conclude that the dynamics are, we have a good dynamics model and we can approximate the dynamics on state distributions induced by various policies. And in order to do that, what we're going to do is we're going to measure the second moment of the true feature on the state at time H minus 1. And I'll explain why this is the right thing to do. Of course, we don't know this thing, so we can't like hope to, okay, you want to make this second moment like big. You want all the eigenvalues to be big. We don't know this thing, so we can't hope to do that explicitly. Instead, what we're going to do is we're going to train our exploratory policy to maximize the learned second moment of the learned features 1 time step even before. So that's why you have to think about all 4. And what I'm going to tell you is that if you maximize the learned features at time step H minus 2, you will approximately maximize the true features at time step H minus 1, which will allow you to conclude that your density model is accurate on any possible role and distribution. That's the idea of the analysis. Maybe I'll try to go a bit fast here. So this is just maximum likelihood estimation. You have your exploratory policy. You take the Hth action uniformly at random, and you get this triple XH, AH, XH plus 1. You just solve the maximum likelihood problem. So you're going to try to find the feature map and the two factors phi and mu that maximize the log probability of the transitions you observed. And other objectives are also fine. This is basically whatever you've used for density modeling before, you can do that. One important point is that it is important that the transition model should have this bilinear architecture. So you really want to embed the state action into a d-dimensional object and take the inner product with some embedding on the other side. So that's going to be pretty important. But you can do GAN type stuff or VAE, or I don't know. I don't even know what everyone does these days, but I think all these things are pretty reasonable. Okay, so that's how you learn the dynamics. Okay, and here's sort of why the dynamics, how to measure the coverage in the state space. So the key idea for these low rank MDPs is this following sort of Bellman backup property. So what I want to do is I want to write, so a policy induces a distribution over the state at time h, and I want to understand what is the expected value of some function applied to the policy's visited state at time h. And the thing is, in this expectation is hidden a transition operator, and the transition operator has this low rank structure. So if I expand this expectation, I can write the expectation, my mouse is not working. I can write this expectation in terms of an inner product, where over here, this is the latent factor, the latent feature that the policy visits at time step h-1. And this is some function that actually does not depend on the policy at all. And so if you think about, so think about this function f as being the model error on the distribution visited by policy pi. So now I can say the model error on policy pi is actually a linear function in the feature map that the policy visits at the previous time. And so the insight here is that if the way you trained the model was from a distribution that spanned all the directions in the feature map at the previous time, then the model error under policy pi should also be small, because I can write this feature in terms of the features I used to train the model. So that's the idea. So there's a robust version where you measure this sort of second moment. So this is the second moment of the true feature at time h-1 induced by the policy cover with some regularizer. And there's some sort of Cauchy-Schwarz type argument where I can write the error of policy pi in terms of the error under my policy cover times some factor, which is like the distribution shift coefficient. So this is what is the inner product between, it's like the feature under policy pi in this norm induced by the second moment of the exploratory policy row. And so this is going to inform what we're going to try to do for exploration. So, this is basically that norm. So what I want to do is I want to find a policy pi that maximizes this objective. Because if I do that and I add it into my policy cover, then it will no longer have a very high objective anymore. And there's this sort of ellipsoid type argument that shows that this cannot be large too many times. But we actually don't know this phi. So we can't actually set up a reward bonus using this phi because we don't know it. So this is where we go back one step in time again. And we plan to visit all the directions of our learned features at time step h-2. So the reward bonus that we use is this phi hat over here. So it's phi hat transpose the second moment in our learned features of the exploratory policy times the feature again. So you train a policy to maximize this sort of quadratic reward, and you just do this using a model-based planner. And what we can show is that this will approximately optimize the coverage objective. So I think this elliptical planner thing is something that I haven't seen too much in the empirical literature, and I'm quite curious to see if it works well. So maybe I'll just walk through it in a little bit more detail. So the idea is we're going to learn a policy that induces a good distribution time step h, little h. And you start with initializing your second moment to be the identity. And for each time, you define this implicit reward. So everything here is in your learned features. So this is your learned feature transpose your current second moment inverse times your learned feature. And you just learn a policy, you just plan. This is planning in your dynamics model. You just plan to maximize this reward function in your dynamics model. And you just check if you can get a high reward or not. If you can get a high reward, you add this policy in. Okay, sorry. If you can't get a high reward, you stop. And you just output the uniform distribution over the policies that you discovered so far. If you can get a high reward, you add this pi t into your cover, and you update your second moment with pi t second moment, and then you repeat. So the idea is like each pi t is going to visit a new direction in the feature space. And so you should expect that there's only like polynomially and poly d of these that you need to find. Okay, so this is sort of the elliptical planner that we use. And what we prove here is that, so we're going to assume a realizability that you have these two function classes. One is for the features, and one is for the left factor, and one is for the right factor. And we're going to assume that these function classes contain the true dynamics. And so what we prove is that you can learn a low rank MDP model that has this sort of system identification guarantee. So what I'm writing here is that for any policy pi at any time step h, you execute policy pi to reach state h, xh, ah, and you measure the one-step modeling error of your dynamics model. So this is your dynamics model right here, and this is the true dynamics. And the one-step modeling error is less than epsilon for any policy and any time step. So this is like truly you've learned a good representation of the entire world as far as any policy can get to. And the sample complexity here is polynomial in the size of the dimensionality of the latent representation, the number of actions, the horizon, 1 over the accuracy parameter, and the function class complexity. Again, other notions of function class complexity are totally fine. And FLAMBE can be implemented in polynomial time. You just have to be able to solve the MLE problem and plan in your models. Okay, let me just mention some potpourri, and then I'll stop a bit early with some sort of parting thoughts. So this is truly a representation learning, because for any reward function, okay, so just by virtue of being, for any reward function, the optimal policy and the optimal Q function for the learned model are linear in your features. And due to this system identification guarantee, this implies that a near optimal policy and the near optimal Q function in the true world are linear in your features. So really, you've learned a representation that allows you to train policies using just linear function approximation after the fact. And this also lets you do things in a reward-free manner, because you just have a model for the world. So if someone gives you a reward function, you can just plan in your model to maximize the reward. And you can use this linear function approximation structure. So you can efficiently optimize any reward function with no further experience. And we also have some other results where you can use like real world planning to avoid needing to sample from your models. But this is a bit delicate because you might not have good coverage, and so you require some sort of reachability assumption here. Let me just wrap up with some parting thoughts. I'll skip this part. This is actually the new stuff, but I'll skip it. So yeah, let me wrap up with some conceptual takeaways. So this is sort of the sort of philosophical or research approach that we've been taking. We're decoupling the structure of the world, like the dynamics, from the emissions or the observations. And I really like this approach. You can sort of imagine there's like a cottage industry of papers you can write here, and we're actually kind of doing that. So we did this paper with Dylan and Sasha and a bunch of others, where we're learning where the latent dynamics are linear quadratic regulators, but the emissions are nonlinear. So again, you still have to use nonlinear function approximation, but the dynamics are relatively simple. And so these are motivated by problems in controls. My colleagues have also done some work on factored MDPs with high dimensional observations. So here you have like a combinatorial latent state. And yeah, you can imagine your favorite problem, you can endow it with high dimensional inputs and see if you can get a good algorithm. And the thing is, like, I like this approach because you can actually conclude, get provably efficient algorithms that rely on nonlinear function approximation. And in some sense, the key idea is that the latent structure enables you to address distribution shift issues or out of distribution generalization issues. These are maybe the same thing. And the way that we've been going about this so far is a very explicit representation learning for discovering the latent structure in your problem, and some sort of reward bonuses using a representations for exploration. And throughout the talk, okay, we saw all but one of these. We've seen issues around like what is the supervision signal you should provide to the algorithm to learn the representation. We've seen these issues of catastrophic forgetting and the need to learn policy covers. And in FLAMBE, I showed you a little bit about this distribution shift issue where you want to transfer notions of error from your policy cover to other policies. We didn't see double sampling, but that's okay. Okay, so just sort of like a hodgepodge of random parting thoughts. I like thinking about these reward-free representation learning signal. And there's many ideas that have been proposed in the literature, like inverse dynamics or these contrastive procedures or methods to try to learn it by simulation. Maybe this is because I'm a theoretician, but I like to think about these things, like come up with toy examples and think about these things and see if you can get them to work in these toy examples or try to break them with toy examples. And I also think it's really helpful to think about what are the Bayes optimal solutions for these sorts of self-supervision. So one thing that I think a lot of people are excited about is using by simulation, but this is a bit delicate. So there are actually sort of lower bounds for learning by simulations. And if you actually have a sparse reward, then by simulation has a Bayes optimal solution that's trivial. So you have to be really careful to try and avoid these sort of trivial or degenerate solutions. And I think just like thinking about little small examples is very helpful for this. A little bit on the empirical side, I think some things I would be curious to try or see if they work is learning dynamics models that have a bilinear form and setting up these exploration bonuses using these sort of elliptical kind of approaches where you try to maximize like the second moments in your feature space. And people definitely try various things. I'm just curious if these things are competitive or better or worse, or perhaps I can understand this in two ways. One is, do these things work in practice? The other one is, do the things that people do in practice, are they analyzable in theory? There's some, I told you about policy covers. I think there's some annoyance there empirically. Perhaps you can sort of do some shared parameterizations or checkpointing to avoid the memory and space overheads here. And yeah, okay, so what I've told you is not really ready to be implemented. And if you look at our sample complexities, they're pretty bad polynomials. So I'm quite curious how to go from polynomial sample complexity to something that you can actually run and deploy at scale. And yeah, we're actually trying to implement some of this stuff. I think there's a lot of institutional knowledge on the empirical side that we're sort of trying to inherit and learn about, and it's taking us some time. So with that, I'll just wrap up. Here are some links to the papers, and I'll just give a shout out to all my colleagues. This is Nan Zheng at UIUC. This is Aditya Modi, who's a student at University of Michigan. Jinglin Chen, who's non-student at UIUC. Alec, Michael, Sham, John, Dipendra, and Wen. Cool, I'm happy to take any other questions. I see one. So you could just auto-encode SA S prime tuples. Yeah, I think some of these things might work. I'm not trying to say that these things don't work at all. I'm just saying, like, we thought about a couple. We came up with some counterexamples. We came up with one that kind of works. Certainly.
Yeah. Well, thanks a lot, Akshay, for the talk. Any more questions from the audience?
Yeah, I have one. Thank you so much for the talk. This is really cool. I'm curious if you've turned your attention at all from state abstraction to temporal abstraction. It seems like that's another direction in which we might hope to compress our RL domains.
Yeah, we haven't done this much. Like my group, not me, have a paper where they do some sort of like hierarchical thing where you use like imitation learning at a low level to learn these meta policies or these, what are these called, these options, right? And then that helps you compress on a temporal scale. I haven't thought about this too much myself, to be honest, but I think it's important. Like our horizon dependencies are pretty atrocious. So doing something better would be great.
So one question on FLAMBE. So is there an implicit adversarial dynamics going on because you assume a low dimensional or low rank MDP? But when you're actually optimizing for the ellipse, right, you're trying to make the singular values be as uniform as possible, right? So you're actually trying to increase the rank of your MDP in a way.
Oh, yeah. So I think you have like this d-dimensional feature space, and you're just trying to make sure you visit every direction. So you're not trying to increase the rank of the dynamics themselves. You're trying to hit all the directions in the ranks that you have, in some sense. Does that make sense?
Yeah, but would that correspond? So I guess what you're saying is you're just trying to increase the number of states you're visiting, but still being low rank.
Exactly. Yeah.
Okay.
Yeah, I think that one is, the elliptical thing is kind of the analog of like, you try to visit like E1 standard basis, then you try to visit E2 standard basis. And that's like exactly what we did in Homer, right? You visit state 1 and then you visit state 2 and so on, right? And this one, you just need to do it in a more robust fashion. So the second moment is sort of the right answer in some sense.
Because it helps you get a better metric space, I presume, right?
Yeah, it gives you sort of this like round. Yeah, you want everything to be round.
Yeah. I mean, it kind of, like smells like a VAE, right? Where you put like this scale, like a prior term saying that I want my distribution to be, uniform Gaussian.
Yeah. I don't know too much about VAEs, but I can believe that.
Cool. Any more questions from the audience? No? Well, if not, then let's thank Akshay for a great talk. Thank you, Akshay. And I guess you have a packed meeting schedule with many people who are very excited to meet you.
Yeah, should be fun.
So do you have the meeting link with you?
Yes, I do. Yeah.
Okay.